Belum.
Belum. Okay, failure theories. Alright. Okay. Okay, can someone volunteer to record? Boleh? Ada siapa-siapa? Abdullah? Alright. Okay, thanks, Abdullah. Okay, in your previous class, I already explained to you about okay, in the previous, you got to be ready yourself in terms of your free body diagram, analysis must be right, okay? And if your free body diagram is wrong, so you punya number component of forces reaction is wrong and your force calculation will be wrong. And then after you got force, we will calculate the stress, either axial stress, either bending stress or torsional stress, everything will be wrong. So then if your stress is wrong, then you relate to strength to get the safety factor, everything will be wrong. So be careful, eh? So because we design, in the purpose we design our component to avoid failure. We want to try our component, any analysis at any point, any section or our component, we want to avoid failure. That's our responsible as engineer. We need to do engineering analysis. That's what we are doing right now, engineering analysis to avoid failure. So today we will learn about failure theories based on static loading. So we call failure based on static loading. Later on, after this, not now, maybe on week 4, we will go for fatigue loading, variable loading. But now we go for static loading. Static loading, it means that the load applied to all your system, your component will be kind of like static. It's not fatigue. Fatigue is, you mean your loading is variation. If we versus time, your variation is frequent variation. Static loading is something your loading is almost to static and pure static. For example, what is static loading? Like the chair, I'm talking again and again, the chair you are sitting on, the structure that support your chair is sustained static loading. The load that you apply when you are sitting on the chair is totally pure. We assume it to be static. Okay, for example, like a bracket supporting a load, for that bracket is, if that loading is just a stationary force, stationary load, so the bracket support static loading. So that is based on static. So in design, we have two cases, either static loading or fatigue loading. Okay, for static loading, so we want to design our component. For example, the shaft, you do analysis a shaft like in your assignment, we still assume on static. I mean that the assignment that you do, we have shaft and we have a pulley system, right? We have a pulley and belt. We consider that one, the shaft is not rotated. We assume it is static. Actually, for shaft is also actually in real case the shaft is for fatigue loading, but we can make a initial analysis first to find the initial value of the shaft. In your case for your assignment, like the shaft, the assignment that I give you, we have shaft and two pulley. And it may actually, in real case, that shaft is rotating. It's because it's power transmission, right? Rotated by motor in drive. Another shaft by pulley and belt is rotated. But in this case, we assume that the shaft is in static case. I mean, in static. That also can be acceptable just for initial guess of to get the size of the shaft. Okay. Okay, our first part of mechanical failures is on static loading. Okay, if you look on if I share you my version of slides. This one, I'm using this slide, static failure prevention. Boleh nampak my e-learning class? Static failure, I'm using this note. Actually, they have version of note. You can use this note also. I'm using static failure prevention, okay? Let me open this slide. Share you. Hold on. Can you see my slide? Lecture 2, failure prevention. Alright. This is on supposed to be static. Static failure prevention. We still on static failure prevention. We're on static failure prevention. Alright. Okay, we are static failure prevention. Okay, that's why at the first part we consider static failure prevention. Static failure prevention. Sometimes in our case, our analysis on our component, sometimes it is static. We look at the what type of loading apply on our component. If the load is static, then we do static failure prevention. Okay. All right. So like you're responsible as engineer, so you got to make sure that you got to make sure that we want to avoid failure. We want to avoid failure. So sometimes when anything failure happen, it will cost life. It will cost life. For example, if you look on this picture, a long time ago, in Sultan Mizan, for example, in Terengganu, right, the stadium, there is no storm, tak ada ribut, tak ada angin, semua tiba-tiba rupture. Itu engineer punya responsibility lah. So it will cost life. So it means the structure of the building, the construction still, the structure to fail. So engineer must be responsible. So make sure when you design something, we must make sure that our design is safe. And we want to avoid failure. So it would cost life. So you get sued. Kalau macam tu, engineer that send all the drawing, semua the document. So itulah you engineer want to kerja professional engineer, right? You want to go for professional engineer, then you will sign a lot of you will check document. Your signature is very valuable. Right? So even if you just sign, people pay your money. This kind of like bribe, like this is not good. Right? So you don't check actually. The analysis is not right. Semua. Sometimes if anything failure happen, it costs life, you get sued. Okay? Be careful. So kita buat kerja kena ikhlas lah, kena betul-betul jalan etika as engineer. So make sure that our calculation analysis right. Macam for example like this one yang at the bottom ni, the structure collapse in Penang, there's no wind, tak ada strong wind for no reason, dia kata, dan dia 4 kereta korban nyawa at the bottom structure ada crane at the top of the building. So ini this kind of example lah. You kat study civil engineer, civil engineer mechanical, they work together lah. Construction steel semua lah. Okay, ini is my part of more mechanical lah, crankshaft, okay, bolt joint. For example, later we will learn how to select bolt and the way we select bolt. That's why analysis must be right. So this pin connection, a connection, a fork connection to the pin, atau the failure happen to, because we must make sure that when we design, when we do analysis, we select material and size of our component must be right. So to avoid failure, right? To avoid failure. Okay, as I mentioned to you, your free body diagram is very important, guys. Kalau free body diagram is wrong, your force calculation is wrong. Kalau force calculation is wrong, you punya stress calculation is wrong. Be careful, everything must be 100% accurate. When you already explained to you, when we have force, we have axial stress, normal stress, and sometimes if we have bending moment, we have bending stress. If we have torsion, we have torsional stress. Sometimes we might consider also at the neutral axis is transverse shear stress. Also, we have direct shear stress. Okay, the stress that we calculated, we have to relate to strength. Okay, I mean the stress that we calculate. For example, axial stress, force over cross-section area, so it's megapascal. Bending stress for solid shaft is 32 moment over pi d cube in megapascal. The stress that we calculate, then we go for more circle. Remember your assignment, more circle, then we get the principal stress. At element that we analyze, or I mean, we have axial stress and we have combination of torsional stress. So we get the principal. In most circle, we get the principal stress, sigma 1, because the stress that we calculate, like bending stress, sigma x, tau x1, okay, ada sound tak sekarang? Sorry ya kelas saya macam ni, saya punya ada problem sikit. Sekarang boleh dengar kelas? Okay, that's why the stress that you calculate, like your assignment, right? You calculate the element, you draw shear diagram, moment diagram, right? So you got your in your case, like the example that I show you, you have XY plane, exact plane. For your assignment, we only have one plane, maybe, if I'm not mistaken, exact plane, or maybe XY plane. So you calculate just one shear diagram and moment diagram at one plane. So you find at point B, for example, is the most, the highest moment that we get. So that we have highest bending at that point. So then plus that we have torsion, right? Combination element at the top too. We have, so it means we have torsion plus bending. So that sigma x and tau xy, that one is still not principal. So you have to calculate by, remember principal stress equation, or you can use Mohr circle, sigma 1 and sigma 2. So that principal stress, we have to relate to the strength. So what is the strength? Strength is the material properties of your, for example, the shaft. If given in the equation, the shaft is AISI 1080. This all a material property. This is specific shaft material by American ASME. They already done this. All material, they have the properties, stable properties on that. So for example, you use this AISI hot roll steel for shaft. So you look at the back of your textbook, you can get the SY value, the yield strength, because shaft is AISI steel. All steel is ductile material. Ductile material, the property, the strength is the SY, not ultimate SU. SY. So we have to relate to the strength. Okay, as I show you, boleh look. Can you look at my live video? Yeah. Sekejap. Okay, kalau boleh, can you see my live video? Boleh? Kelas? Boleh nampak Okay. Kalau if you, for example, like for ductile material, most of our component is ductile material. What is ductile material? Ductile material is steel, mild steel, carbon steel. Most of our mechanical component is ductile material. Steel, aluminium also ductile. Ductile, ductile material, they at certain, remember when you do specimen test, remember dulu your lab, remember your strength, standard tensile test, universal tensile machine, right? Universal tensile machine, you apply direct force. For ductile material, okay, you boleh nampak my drawing Okay, strain, strain over stress. What is strain? Strain is delta length over length. It elongate. When you apply the force, it will elongate, right? So for all ductile material, the first zone is become straight line, right? Okay, it means your stress, force is proportional to your stress. Kalau this is force, your stress here is, of course, the axial stress, right? Force over area. Okay, when a stress increase, the strain increase, so it becomes straight line. But for ductile material at certain, if it reach, okay, at one point, this one is a straight line. But at one point, then it reach, if the stress, if the force is until at one level, it increase, then it become, then the your specimen ductile material, it will become like this one. They have a peak here, and then it goes down and it reach up, and until it rupture like that. This is where it breaks. Okay, so at the point here, when you reach the limit of your ductile material, this is what we call the yielding happen. At this point, yielding happen. Okay, yielding. I mean, once the material ductile reach it yielding punya limits, so it behave like plastic. After yielding, it longer kind of solid. It become more elastic, more like elastic, like plastic behavior. So it will elongate. So it become weakened. It will become weakened. That one is ductile material. So the limit for ductile material is here. This is what we call SY, the yield strength in megapascal, because strength is stress lah. The limit of our material is SY value. So that's why when you choose material, you look on table property, what is the SY value? For any ductile material, you don't use SU. But this one at this point it will rupture. But the most maximum here, actually there's a maximum KD is SU. We don't consider for ductile material SU. Correct. Sorry guys, boleh nampak Okay, for ductile material. Okay, for ductile material, it means we don't use SU. SU is the most ultimate lah. Sini the rupture the lowers little bit. Tapi up to this level, okay, it's lower than SU and the rupture point. For the limit for our ductile material is SY. So SY you can get from the table properties at the back, or your in the appendix in your textbook. So that's why when we calculate the stress, we relate to the strength. So what is the strength of our point that we analyze? The material that we use, okay? The material that we use. Understand, class? That's our strength. Okay, strength is mechanical productive material. So this is ductile. Ductile we use SY, the yield strength. The yield strength. So because any ductile material, if the stress that we calculate, you analyze this point, you calculate. Let's say it's a pure axial stress, sigma F over A. Kalau sigma F over A, for example, in your case like this, just a pure stress. You specimen, you punya component like this, it's just a pure tension only, pure tension. Is your F, okay, F, and this cross section is a round. So for axial stress for solid round is force over A, and shortcut formula is for F over pi D square, right? Pi D square, and A is pi over 4 D equals to 4. Sorry. Force for apa D kuasa 4, sorry, not pi D cube, pi D kuasa 4, okay, 4 D kuasa 4. So this is axial stress, okay. Area is 5 over 4 D over 4. So shortcut formula of F. Okay, when you calculate this in megapascal, the axial stress, if that axial stress you plot it, if you punya value of your stress is within this zone, see dia tak reach this selamat, still safe. Tapi if you punya axial stress is greater than SY value of that property, katakan property you select this one EAISI 1020, you can get from the table at the in the appendix. If you say the SY value is 400, for example, 420 megapascal from the table. So you calculate, let's say you calculate your case is 120. So it's still safe, it's lower than your yield strength of your material properties. Understand, class? So safety factor tu basically logic macam tu lah. Safety factor, this is general safety factor, your SY value over the stress axial that I calculate in my case. If my case is a pure tension. Understand, class? Class? That is safety factor. Kalau greater than 1, understand? That's what we call safety factor. Because the purpose here, we need to get the safety factor. If safety factor greater than, actually 1 is a margin of error. Greater than 1 is safe. Okay, that's the meaning of this lah. Mechanical static failure. That's what we do. Okay, mechanical property. If you look on the slide again. Okay, that's what I'm talking about. You punya limit when you press all ductile material. Nampak tak, dia sampai at the reach SY, they become decking. Then kemudian they little bit lower, then it come here. Then this one is ultimate. Ultimate is not for ductile because ultimate is the most loading applied until it just little bit lower and fracture and break down. You punya ductile material, it breaks. So yang ni, the limit yang sini, up until the yield strength that already you punya tu dah weaken, the material of you punya, your component is ductile already weakened. So the ultimate, dia punya limit, the strength is SY, not SU. SU only on brittle. Okay, if you look on brittle punya stress strain punya distribution, so what is brittle? Brittle material, what is brittle? In our machine component design, rarely we use brittle lah. Brittle ni, for example, like for brittle material ni rapuh lah, benda yang rapuh kan. For example apa? Kalau metal apa dia? Brittle material. Steel, mine steel, carbon steel, all is ductile, or shaft, semua lah, all is ductile material. Brittle material, for example apa? Cast iron. Cast iron is brittle because cast iron they pour the molten iron into the die kan, acuan kan, the mold. That one is not ductile, it is brittle. Powder metallurgy, powder metallurgy also brittle. Like glass, brittle. Cast iron, powder metallurgy. Okay, that is a material they use powder metallurgy. Powder metallurgy meaning they pour the powder and they heat it into the mold. And that's also brittle. Glass, of course, is brittle. Okay, so brittle material, dia punya plot of you punya stress strain is not like that. They don't have a necking. Dia tak ada elastic. Pasal dia brittle, dia rapuh. If you plot the strain, okay, your strain and your stress, kalau brittle, dia like this. Dia tak ada necking. Dia sampai at this point, and this one ultimate. Ini terus dia rupture terus. Pasal dia brittle dia tak, dia brittle material is, kalau kata. Okay, sorry. Okay, I continue again. For brittle material, the plot is like this. The plot is like this. You punya porcelain, dia tak ada netting yang terus ada. Because brittle material, dia kan rapuh lah, brittle material. When you apply force, dia totally, until ultimate, then it will break down. Because there is no signal. Kalau you design, be careful. When you use brittle material, for example, bracket, do not use brittle material like cast iron. Brittle material only good. What's the purpose? What's the purpose of cast iron ni? What's the benefit of cast iron? Like they only for casing. Pasal the way they manufactured for brittle like cast iron is quite cheap compared to forging like ductile material. Macam shaft. Shaft is not using by casting. Shaft is by rolling, hot roll. So the process to make the shaft is kind like costly, right? They have a lot of operation. For cast iron, it's just the pour into the mold. That's why they're quite mean. And it's a pure cast iron. So cast iron ni only normally for casing. Remember, for example, in centrifugal pump. Inside your pump, you have impeller shaft. All impeller shaft, everything is a ductile material. Impeller, if I'm not mistaken, impeller also is ductile. Your blade. Blade is pasal you have a lot of force. I'm not sure whether it's not. Only the casing of your pump. Remember, kan pump you have casing. Casing, we have two casing lah, join together to enclose you punya pump inside, shaft, blade, impeller, turbine, everything. That casing, the casing tu yang brittle lah, they use cast iron, they don't use steel, because steel is more expensive compared to cast iron. Steel is ductile, right? So for casing, just casing purpose, the casing, I mean the surface is rough, they don't need to be shiny and smooth, like casing of the pump, casing of everything lah, your piping, they want cast iron. Like shaft, internal that sustain load, have rotation. When you mount your bearing, you mount your gear. This kind of component is ductile. Okay. So this is brittle. Okay, understand, Claire? Alright. Can you see my slide? Boleh nampak slide saya?
Boleh, Doktor.
Okay, that's I mentioned. If you look at on ni apa tu? Strength lah, strength. You calculate your strength related to your strength. Strength is a property, material properties lah from your table. Strength. You material, what material you choose, you look on the table. What is the material that was SY. For that time you use SY, yield strength. Okay, static load ni, as I mentioned to you, we are still on static loading. Stationary force, moment or member apply at your component. It can be axial, compression, tension, bending load, torsional load, and combination of them. Normally, banyak case in shaft combined. Remember, when you do your assignment, you have sigma X combined to your tau XY. I mean, you combine with bending stress and torsional stress. Then you get the principle. Nanti I explain to you. You must find the principle. So already explain what principle. Principle can get from Mohr or sigma 1 equal to sigma X plus sigma Y over 2 plus square root sigma X minus sigma Y over 2 square plus tau SY square. That is sigma 1. Sigma 2 is sigma X plus sigma Y over 2 minus square root sigma X tolak sigma Y over 2 square plus tau SY square. Okay, already formula already given. You can simply do, sometimes you don't have to do Mohr. You just get your sigma 1 based on the equation and also your tau max. Remember tau max. What is tau max? The radius of your Mohr circle. That is the tau maximum. Tau max is what? Sigma X minus sigma Y over 2 plus tau SY square root of that. Check balik the equation, tau max. Okay, that's the penting. Sigma 1, sigma 2 and tau max you calculate. Then there is the equation how you get a safety vector. Pasal that one is principal stress. The sigma X and tau SY that we calculate on our element at the beginning, that one is still not principal. Okay, as mentioned, sometimes the load is static to gerak idea. Macam for example, the shaft, you punya shaft assignment that I give you for that one, the shaft we have pulley and two set of pulley. Actually, that shaft tu sebenarnya is, that one is fatigue loading. Itu later on week 4 we will learn. Variable because the shaft is rotated. Tapi kita can get rough idea what is the size of the shaft. Boleh, you can do that also. Actually, that shaft tu sebenarnya shaft is rotated. Tapi sometimes we want to get rough idea the component dimension. We can assume it's static. Okay, and also when variation of load are few or minor in nature. For example, like you design a footstep, it is not, kita can assume static. For example, when you design, for example, like a bracket that sometimes like you, for example, like I mentioned again, a footstep and a bracket, you have a footstep, a pedal, then you step on it, and kemudian you step on it, then you do your work lah. Macam construction worker, they do unloading off the, do the things, and then they step down, then they step on the footstep. No, you mean the footstep, when people step on it, they have loading. Then sometimes people not stepping on it, so they don't have loading. So mean the variation to it quite low. So we can consider that static. Tetapi kalau you punya loading of your is frequent loading and the loading is variable, fluctuating, they have maximum value, minimum, that one we consider fatigue. Itu later on you will learn on week 4 about fatigue loading. We still assume static. Okay, so in design that I mentioned to you, you calculate, tadi I mentioned kan, you can, free body diagram must be right, then you calculate your forces is right, then your stress will be right, okay, then the stress will relate dengan the strength, the SY value of journey, then we okay, boleh dengar sorry galah macam ni selalu. Boleh Alright. Okay, there are two approach of design approach. Okay, normally the easiest one is number 2. You select material. Okay, macam like your assignment, material is given, the dimension is given, the diameter of the shaft is given, and then you find the safety factor. So if your safety factor less than 1, it means it's not safe. So you have to increase the dimension of your shaft. So you get 2.70. It means it's safe lah. Okay, this is the most easiest approach lah. Normally student do it like this. Tapi the best approach is like this. Okay, your safety factor is given. You design, for example, you design shaft. You design shaft. For example, like in your assignment, the shaft. You design safety factor, you put it 4. Jangan put safety factor 100 guys, too waste lah, too much. For example, like on the safe side, when you do static loading, you go for 4. I didn't say 1 point something. I didn't say 2. You go for 4 because maybe pasal shaft tu, like shaft tu is actually is fatigue loading, right? We still on static. Okay, you design safety factor. Let's say you put it 4 and you select the material. You want to use AISI 1020 and the punya SY value for 200. Okay, let's say 420 megapascal from the table. Okay, so you know the safety factor and you know the strength. So from then, your calculation nanti when you buat shear diagram, moment diagram, you punya shear, you punya stress that you calculate will become variable in diameter of shaft. So it means, but you know the safety factor is 4. Since we know safety factor is if our SY value, SY is already given, we get further over your stress you calculated. It means safety factor is strength SY over the stress you calculate. It means your stress that you calculate because you punya you don't know yet in variable of diameter, but you know your safety factor is 4, so you know your diameter lah. So this is the most accurate lah, most safe. It means you don't have. Kalau approach number 2 ni, you select dulu dimension of your shaft and you select the material also and you find, then you find out your safety factor is close to fail. Let's say 1.1, it's not good. Okay, so you have to redo it again, recalculate again. So that one is number 1 is much better lah. Understand client? There's 2 kind of approach. Faham Right? Okay. Okay, safety factor. That's why I talk about you. Safety factor is F ultimate over F lah. And F ultimate because F ni relate to stress. Actually we calculate stress lah. Equal to sama juga you punya strength. F ultimate ni, remember you punya plot stress rate. You emit F ultimate. So when you do tensile ties kan, tensile ties actually is a force. For example, yang you punya tensile ties is your force lah. Called is axial stress, right? You punya tensile test, kalau you punya specimen, this is your specimen tensile test kan. Standard tensile test is force. Actually force is really stress, but stress over area. You plot, but you plot sigma over strain. So actually the force, you mean kalau elastic like this, then you necking, that one your SY value then like that, like this. So ini your SY. Ini F, it actually force lah. Pasal tensile machine the force, tapi you relate buat the graph based on stress, force over area. This ultimate is your SY value lah, but in term ini SY lah. Understand client? Ultimate is the force, it become SY. For data material, ultimate. So it mean kita calculate relate to stress lah, because strength, because they have strength. Dalam table property strength in megapascal, so we relate dengan stress. So kalau kita punya element is only pure axial, sigma axial like at the bottom here lah. And ini the SY value table properties. That your safety factor. Okay, strength over the stress. The stress that you calculate. If you punya stress is lower than your strength, it means it is safe. Theoretically, it's safe. Okay. Also, sometimes in our case, we have torsional stress. Kalau torsional stress, I mean our limit value. Kalau D is sigma, limit value is SY. For this one, for torsional stress, tau. Torsional stress, sometimes in our case, is like this. Okay, our case, like if you look on my live video, sometimes in our specimen, kadang-kadang they have pure torsion. And this is our specimen, we have pure torque like this. Pure torque. It means at any element here, our element here, E here, we have pure torsion. And this one go up, and like that, like that. Okay, so when we plot our Mohr circle, our sigma is 0, x, and y also 0. So it means our x is here, and our y is here. Okay, our y is pasal clockwise. So kalau kita plot Mohr circle is like this. Kita punya tau versus sigma. This is a pure torsion. Pure torsion. Kalau pure torsion it means you punya safety factor, you punya pure torsion you punya shear strength, not shear strength over the tau. Ni tau max lah, tau max from Mohr circle, the radius is your punya tau, this is your tau maximum, right? That is also can relate that shear strength. Shear strength. Shear strength. So what is shear strength? Shear strength nanti ada value dia. Pasal shear strength ni you can look on the table. Biasa dalam table properties at the back they only give SY value of any material, dia punya yield strength and also the ultimate SU. Remember SU for brittle. SU is the most until before the rupture. Tapi pada data itu we use only SY. Okay. Okay, so that's why shear. Okay, sorry boleh semua. Okay. For shear strength, dia punya ni shear strength SSY ni you rarely sometimes in the table. Kalau if not in the table, you based on what theory? Later I explain to you. We have DET theory, MMSC theory. MMSC theory say that shear strength is 0.5 your SY, but if DET is the most accurate is 0.577. 557. Sorry, 0.5. Sorry, saya tak boleh call 5 nanti later on. 0.577 SY. That your shear strength. Then over your tau maximum. Okay, this is basically general explanation about safety. Actually, this is not I explained to you about theory. Different theory, different equation. So this is a general equation. Okay, general equation. Okay, shear strength over shear stress. Alright. Okay, we have three theories, guys. We have three theories. The first theory, if you look on my slide, is maximum normal stress theory. Maximum normal stress theory means, okay, actually maximum normal stress theory is good for brittle material, to predict failure for brittle material, because maximum theory is cakap the greatest tensile. Tensile strength mean ultimate strength. Ultimate strength. Remember that I explained to you, kalau brittle material, when you plot strain over stress, dia tak ada yielding. Brittle material like cast iron, they don't have yielding. The straight line like this, and until the curve like that, and become this is ultimate lah. The ultimate. This is the ultimate. Or we call it ultimate lah. SU. This is not yield strength, right? This is ultimate. Your SU value. So you punya, kalau MNST good for brittle, dia cakap kalau the stress you calculate reach SU, so failure will happen. Ini for brittle. Only good for brittle. For brittle material, you use maximum normal stress theory. Maximum normal stress theory. So it means your stress that you calculate, dia cakap the principal stress. Nampak tak in my slide? Dia tak cakap. For example, kalau katakan you punya specimen ni, you ada bending kan, you ada bending like this moment, and you ada torsion also, you ada torsion. So you punya element tu you have sigma x, and you have torsion like this, and drive like that, torsion. Remember you do Mohr circle, right? When you do Mohr circle for this case is you have, okay, for this case you have macam ni kan. Okay, that's why kita still tak sigma x, this still not principle, guys. This still not principle. So you have to go for principle. Remember, Mohr circle sigma over tau. Okay, and this one for x axis, so we have value for x, and this one clockwise is positive, clockwise is positive. So here is you punya y value. Remember, yang ini you already calculate lah. Kan yang ni 32 moment kalau shaft pi d cube, right? Tau SY is 16T, like in your assignment, 16 d cube. So you got all the value in megapascal. You plot in more circle. So the X value, Y value, we don't have sigma Y, and we only have, okay, this is like this, and this one is counterclockwise. So Y value, so is negative counterclockwise of your punya ni. So this will be your Y. So you punya plot, you punya more circle is like this. Are you watching, guys? Hello? So ini yang principle. This is principle, guys. Sigma 1, this one is sigma 2. Okay? Sigma 1 and sigma 2. So maximum normal stress theory, either your sigma 1 and sigma 2, okay, they plot. Okay, this is more circle sigma over tau. Sigma over tau. But if we plot, so we get our sigma. Actually, sigma 1, you can get equation beside more circle, you can get what? Sigma 1 is sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 square plus tau xy square. That's sigma 1. What is sigma 2? Sigma x plus sigma y over 2 minus sigma x minus sigma y over 2 square plus tau xy square. Since no sigma y, no sigma y, we only sigma x. So we got sigma 1. Beside more circle, you can do by calculate. Sometimes you don't have to use more circle, you can see lah you punya ni. Okay. Sigma 2, you get your sigma 2 value. Sigma y is 0 in our case. We are by exercise, we only sigma x and tau xy. But so that sigma 1 is what we call principal stress, but maximum normal stress theory. So when we plot, maximum normal stress theory, this is a plotting, not sigma. This is not more circle. Sigma 1 versus sigma 2 versus. Okay, kalau sigma 1, your sigma 1 cannot reach maximum normal stress theory, you punya border, sigma 1 ni border ni you punya SU tension. Pasal material dia ada ultimate tension and ultimate compression. Sigma 1 dia punya boundary dia when you tensile, in tensile, not compression. In tension, sigma 1 that you calculate cannot reach the border ultimate of that material, SUT. When in compression mode, sigma 1 cannot go more than, betul kita cakap nak go more than you punya SU compression. Also go for sigma 2. Sigma 2 punya value cannot go more than SUT value, and sigma 2 also not go more less than kalau in compression mode, SUC, because material they have ultimate compression and ultimate. Alright, ada line Okay, boleh dengar? Kelas, boleh dengar? Boleh. Okay. So if you look at my live video ni, so you punya limit at sigma 1, SUT and SUC. Okay, SUC. Pasal any material dia ada value of ultimate tensile and SUC. You look on the table, ultimate tensile and ultimate compression. So either your sigma 2 and sigma plot mesti within this zone. This is M and ST, M and maximum normal stress theory. Maximum normal stress theory. So I mean when you can do, you can find safety factor by using plot of this. You buat this pure graph lah, based on graph. You buat graph and you plot your where is your sigma 1 value. This is your sigma 1. What is your sigma 2 value? In my case macam ni, sigma 2 is negative, right kan? Sigma 2 is negative. Okay, sigma 2 is negative. So it's within this zone. Within this one, selamat. Within this zone, selamat. Understand tak, guys? Nampak saya punya ni? Within this zone, selamat. Okay, how we get safety factor? Safety factor like this, guys. Katakanlah I go for positive sigma 2 lah. Sometimes you get confused. In this my case, okay, positive. Okay, this sigma 2, sigma 1. Okay, this is your point. You analyze, you punya case is here. So safety factor, this is your border. Border is like a square, right? Okay, it's a rectangle, actually not square, guys. Pasal SUT is lower than SUC sebenarnya. Brittle material, SU tensile dia lower than SUC. Tapi in this case like this, rectangle. So safety factor is like this. You buat straight line. This is your loading point. You increase the begini. So from here. So yang ini adalah value of your S2. Ini adalah sigma 2 lah. So safety factor is S2 over sigma 2. Also, the limit here, this is your S1 of course, SUT kan. S2 ni adalah you punya value ni. Yeah. Here, this is S2. Ni S2. Pasal ni adalah graf sigma 2. Also safety factor equal to S1 over sigma 1, ratio sigma 1 over sigma 1. Same thing. Pun model you can use this like this check. You can check like that. Tu this you punya border of you punya M and ST. Okay, if you look back at the slide, PowerPoint, look, check balik your PowerPoint, as shown in your PowerPoint, you nampak the SUT. Tapi yang this one in this slide, SUT tu lower tu as I mentioned. Okay, this is a more circle, more circle sigma over tau. Okay, then you get your, okay, you mean your more circle, the more circle to limit the SUT and SUC, because this is sigma 1 and sigma 2. Okay, safety factor for ni, for maximum normal necessary, kalau you don't plot sigma 1 like I show you plot sigma 1, so you can use formula. Formula is SY over your sigma max. SY over your sigma max. Ini kalau SY ni kalau actually is for brittle material. Brittle material don't have SY, tapi sometimes you want to use for ductile. Tapi rarely kita use lah. For ductile you want to use for ductile pasal the strength is Y over sigma. What is sigma max? Your sigma max is the you punya sigma maximum the most principal. Ada sigma 1 and sigma 2. Which one is the maximum? Which one is the maximum? Ataupun you punya SU over your sigma max. Okay, SU over your sigma maximum. Okay, itu adalah untuk MNST, SY over sigma max. Kerana kalau you nak use for ni, katakan the question ask you to for MNST, tapi rarely happen, SY over your sigma. What is sigma max? Sigma max tu you calculate, sigma 1 and sigma 2, which one is the greatest? If sigma 1 greater than use sigma 1. Clear tak guys? Okay, tapi kalau brittle material you don't use SY, you SU over your sigma max. Ini kalau you use formula. That is for MNST. Alright. Okay, the next theory. Okay, uniaxial tension, uniaxial compression punya ni lah. So ini you punya combination of you punya tu lah. Okay, principle support more circle must lie within this bound to avoid failure. Within you punya principle more circle ni. Principle maksudnya the most ultimate more circle lah. You punya plot sigma or tau within the SUT and SUC. Ni I mentioned to you tadi, kalau sigma 1, sigma 2 plot, you mean your sigma 1 and sigma 2 plot is within this boundary. Actually, you punya ultimate tensile ni is little bit lower than value ultimate compression. And atomic compression. So sigma 2 within this boundary you plot. Kalau it's within this zone, it means you punya point of analysis tu is safe lah. Okay. Okay. The next theory is maximum shear stress theory. Sekarang boleh dengar saya ke kelas? Boleh. Okay, if you look on your ni, maximum shear stress theory. Okay, ini only used to predict yielding. It means it good for ductile, not for brittle. Maximum shear stress theory is only for ductile material. Okay, sometimes kalau you punya question ni, sometimes they ask you to find. Okay, boleh dengar Okay, if you look on my slide, maximum stress theory only good for ductile, only used to predict yielding, and it's not for brittle. Maximum stress good for ductile material. Okay. In maximum shear stress theory, say that maximum yielding begins whenever the maximum shear stress in any element, the one that we analyze lah, maximum shear stress. Okay, maximum shear stress becomes equal to maximum shear stress in a tension test specimen of the same material. Means tension, okay, equal to the maximum shear stress in test specimen. Okay, if I want you to check, kalau standard tensile test, tengok sini. Standard tensile test. Standard tensile, okay, let's say like my specimen is like this. Ni is standard tensile test lah. Pause, you can look at my live video kan. This standard tensile test, specimen. So ni this is your element. Kalau you punya element is like this lah. Element is you punya element. And you have only standard tensile. You don't have torsion. You only have sigma axial lah. Sigma axial only. Okay, sigma axial. So when you plot your Mohr circle, sigma over tau, what happen? You punya x-axis here, you have sigma, this is your x point. Your y-axis, nothing, 0. Betul tak? Class? Are you listening? 0, So your punya Mohr circle is like this. Circle like that. Circle. Tapi origin is here. Dia standard test ni punya. Okay, if you look, dia cakap maximum shear stress is said that whenever the maximum shear stress become equal to the maximum stress test standard test, maximum, okay. Standard tensile test already done for material certain. So this is your punya tau maximum, betul tak? The radius of your Mohs circle is same as this is your sigma 1. Sigma 2 is 0 here lah. Sigma 2 is 0, sigma 1. This is your tau max. Kalau the tau max, the shear stress you punya that you analyze, you punya tau max, okay, this is standard tensile test. Tau max, kalau standard tensile test dalam dia run, tau max ni adalah you punya tau max ni adalah kalau tengok, kalau sigma 1 for ductile, kita punya sigma 1 limit value dia apa? Sigma 1 cannot reach apa, dia start yielding, apa dia? SY, betul tak kan? Are you listening or not? Hello class? Are you listening? Sigma 1 ni, dia punya limit value SY, right? Tau max, kalau standard tensile test, kalau kita standard tensile test, sampai SY value, dia punya maximum limit of you punya Mohs circle, SY, right? Sigma 1. Okay, then only value, okay, start yielding kan? For ductile, for ductile. Okay, in that case, kalau this is SY, this is your tau max ni equal to what? Relate to SY. If you look for a Mohs circle, SY over 2, the radius of your Mohs circle, betul tak guys? Okay, if sigma 1 ni, the maximum dia punya limit is SY, right? Standard tensile test. So your tau max is SY over 2. So any element, katakan you buat tadi macam you punya assignment, you have sigma x, maybe you punya case not pure tension, this pure tension yang dia cakap lah, sigma x you have combination of tau xy and you go up like that, it balance like this, tau xy, then you get you punya plot circle, Mohs circle is different lah, you punya Mohs circle, okay, sigma, you have value sigma lawan tau, you punya Mohs circle, you have one value of you punya x, and ini kalau y is positive, and you have one value here, and for y you know have sigma 0, and you punya ni counter clockwise is negative, go here, okay, then you got you punya sigma 1 here, and sigma 2 here, and you mean, okay, this is you punya case ni, tau max, you punya case, your tau max that you analyze, this is your analysis, this one standard tensile test yang ultimate sampai ni, okay, standard tensile test is like this. Kalau the tau max yang you calculate here, actually you can do, I'm showing you Mohs circle, actually you can get formula kan, tau max kan, when kalau you ni you get tau max, can remember formula, sigma x minus sigma y over 2 square plus, if I not, correct me if I'm wrong, square root of that, betul tak kan? Betul tak guys? Tau maximum equation principle ini kena ada, I already in the learning I already put it class, you can get this. Tau max dia clear, actually Mohs circle is like this lah. Tau max, if this tau max dia reach apa cakap, the maximum shear strength dia become equal to you punya tau maximum yang ini, tau maximum yang dia sudah kalau brilliant. Okay, that's why maximum shear stress say that the maximum shear stress in element yang you analyze become equal, you punya tau max ni equal to value of SY bagi 2, failure happen lah, itu border dia, that's the border. The tau max that your analysis relate to standard tensile test, your tau max equal to SY over 2, the value, katakan you tengok your material properties, what is the SY value, divide by 2, that is your tau maximum. Okay, if you get that one, you punya tau max that you calculate is greater than that one, fail happen lah, it will fail, maximum shear stress, sorry, understand tak? Faham faham kelas? Means maximum shear stress said any element, macam remember your assignment, it's like this, right? Lebih kurang kan, your ni, you got your tau max, you can do it by formula atau Mohs circle, you find your tau max. If tau max value in megapascal Compare to standard tensile ties punya muscle of your material, your material. So material tu you standard tensile ties, kalau you punya SY, sigma 1 is SY lah. So tau max is SY over 2 based on this standard tensile ties punya muscle is like this. Standard, you only have pure tension only. So you punya muscle is this. Consider sigma 1 ni reach SY. You punya tau maximum is SY over 2. Clear? So it means the tau max that you calculate ni is greater than SY over 2, it will happen fail. Ini you punya border. Strength you only SY over 2. Understand? Okay. So that's why if you look back in my slide, that's what I'm talking about tadi. Ini standard tensile test lah. Unit to unit tension, tau max SYT lah. So sigma 1 SYT lah, border of your sigma 1 SYT, you punya tau max. So tau max is SY over 2. That's what I'm talking about tadi. In my slide. So SSY. So tau max is SY over 2. This is your strength ultimate. Tau max ni, so if this is ultimate yield strength over 2, tau max adalah shear strength. That's what I call it, shear strength. So SSY. Understand? So tau max to your SSY equal to 0.5 of your yield strength of your material. So SSY ni shear strength. That's what we call shear strength. Faham? Shear strength. Okay. If you look back in my notes, okay, my last video, okay, safety factor, kan saya cakap, shear strength, kalau shear strength over tau maximum. Kalau shear relate to shear, pasal kita calculate tau maximum, principal strength, we do calculate tau maximum, shear strength. Kalau shear strength in maximum, shear stress theory is 0.5 SY over your tau maximum ni, the one that you analyze. The one that you analyze, you do your assignment, you calculate the value of your tau max. Okay, then you put your tau max will be in your denominator. Then upper nominator you punya ni is your shear strength based on MSST guys, 0.5 SY. Not DT, DT 0.5, 0.577. 0.5 SY. So MSST theory, safety factor is 0.5 kan SY over 2 lah. So SY over 2 tau maximum. Ni equation ni. Faham? Plus. Okay. So this is MSST. This one only for ductile. Good for ductile. Not MNST. MNST for brittle. Okay. Remember. Okay. For ductile. Sometimes in your question in your exam, they ask you to find safety factor in both theory. MSST and also DET. DET ada one. So that's why if you look back in the slide, so you punya zone sigma 1, sigma 2 plot is like this. Dia no longer dia become a rectangle. Dia bukan rectangle. Dia bukan square. Sorry. Dia like this. Dia like this. So you sigma 1, okay, sigma 2 plot is like this. So you punya, ini adalah pasal dia ada border. Sigma 1 always, dia ada ultimate. Sigma 1 ni sebenarnya, any element dia ada border of yield strength and border of yield compression. Memang standard tensile test they do compression also, not just tension. Compression, I mean they force to the compress until the yielding, dia become the necking to become wider lah, dia ada. Tetapi dia ada SYT. So limit, so SYT and SYC. Also sigma 2 also SYT and order is this one is maximum normal stress story, but for maximum stress dia diamond shape. Diamond shape. I want to make it short lah, don't ask me apa dia, but ada explanation ada why diamond. Pasal ni ada shear diagonal line, so you ada limit. So you punya diamond, you punya border is here. This border, okay? This diamond shape. So when you plot, katakan you calculate you punya sigma 1, you do analysis yang tadi kan, you buat analysis, your assignment, you calculate what is your sigma 1. Remember you do analysis, sigma 2 you plot. Okay, sigma 1 here, sigma 2 here. So this is your point. So it's safe. Okay, the line. Alright. Jadi kalau you plot graph ni, sigma 1 over sigma 2, you can do it. If your point is within zone selamat, you can do safety factor by this also. So yang ini, this is sigma 2 punya graph. So this one will be your strength 2 lah. This is your, this is your sigma 2. Jadi is your sigma 2 value kan. So yang ini, so you reach the border ya, yang ini adalah this is your strength 2. You can do that safety factor is S2 over sigma 2, ataupun here ini adalah sigma 1 value, SYT ini is your boleh kita consider S1 lah. S1 over sigma 1 pun boleh juga, ataupun the equation that tadi, the equation is safety factor. Kalau you use equation for MSST, safety factor is SY over 2 tau maximum. Okay, that is MSST, maximum shear stress story. Clear Okay, ini only for ductile. Okay, alright, boleh ke dengar soalan kalau kelas? Okay, the next theory, okay, distortion energy. Okay, ini actually yang kita use sebenarnya. Tapi I need to explain to you all other theories tu lah. MNST, MSST and distortion energy theory. Distortion energy theory, okay, this is one the most accurate untuk to predict ni lah for ductile, best to predict failure in ductile material, because pasal shear stress theory dia cakap based standard tensile ties, it mean you punya stress, maximum stress, you punya analysis, you punya tau maximum kalau equal to SY over 2, that is the border dia lah, must not greater than SY over 2 based on standard tensile ties. Tetapi distortion energy theory dia tak pakai that kind of theory, dia pakai dia cakap equivalent stress, dia calculate the equivalent stress, equivalent sigma E, it mean the energy equivalent tadi, the kind distortion energy, it's kind like distortion energy that it will change the shape of you punya specimen that you analyze, but not the size. It mean the size remain the shape, the energy that change the shape, that we call von Mises stress. Von Mises stress, the energy that the stress happen, we relate to stress, equivalent stress. This is the stress that it have the tendency to dia punya to change the change the shape, but not the size of your punya material. They change the shape because of the stress, your combination of torsional bending stress. You find that von Mises. Kalau that von Mises stress tu you calculate that, what is that von Mises stress, di itu sebenarnya sigma E itu von Mises atau we cakap equivalent stress. Sigma E itu mas ni lah, kalau dia punya limit dia greater than your SY, so it will fail lah. So make sure that you punya sigma E that you calculate tu is not greater than you punya, because ductile material, pasal DET only for ductile, best to predict failure in ductile material. Okay, it's good for ductile, accurate for ductile. For ductile material actually we go for DET lah, number 3 punya theory. So you got to calculate dulu your sigma E dulu, your equivalent stress, already shown in the slide. Okay, in first case, if you have triaxial stress, you have sigma 1, sigma 2, sigma 3. Triaxial stress ni you have sigma 1, sigma 2, sigma 3. Actually guys, kalau you punya plot more circle, dia ada sigma 3. In our case macam kita have sigma 1, sigma 2, ni sigma 3 is 0 macam tu, we plot our more circle, sigma 3 is 0. Ini kalau sebenarnya we have sigma 1, sigma 1. Actually we have other case we have triaxial stress. So what is the case yang ada triaxial stress? Triaxial stress ni yang case where, for example, like if your element I put into 3D like this, so this is X, this is Y, and this is Z. Other case where you have, okay, ini based due to bending stress, you have sigma X, and this one due to other stress because of the radial stress sigma Y. Ini pun rarely kita ada happen. Yang ini ada sigma Z. Sigma Z due to the pressure. Due to pressure. This case macam element like this, like pressure vessel lah. Pressure vessel lah. This more complicated calculation. I mean you have internal pressure, pressure tank vessel, you have internal high pressure in that. The element at the surface tu, you have to be careful lah. They have both axes lah, sigma X and sigma Y. Sigma Y due to the radial. If you look on the side view, due to the tension of the, because of the pressure inside, it could produce sigma Y, and with sigma X elongate of the in term of length, because of the pressure vessel inside sigma X. So they have both cases, sigma X, sigma Y. In this case, you have value sigma 1, sigma 2, sigma 3 lah. Tapi kita rather in our case, kita boleh our case for bulan itu by SSR. Guys, are you watching the slide or not? Class. Okay, the number 2 ni, kita pakai yang number 2 yang we have only by access. Remember you punya assignment kan? Your assignment kan you only have you punya at point B tu the most your moment diagram, so you have sigma x, kan? And you have tau sy like this. I assume like this tau sy. Remember you punya assignment for shaft kan? Sigma x is 32 moment pi d cube. Be careful moment at B to combine both plane. In your case assignment that I already give you only one plane, right? The assignment that I give to you one plane. Tapi normally the example that I shown you in class, two plane. Moment at B, two plane. XY plane square plus exact plane square. That is the moment here. Pi d cube, so that will be your sigma x and your tau xy is 16 top over pi d cube. Okay, torque is remain the same lah. No play pasal torque along the circumference with the same value of torque. So torsional stress tau sy is 16 kilo pi d cube. So what I mean, you already have sigma x, so sigma y, then you can calculate your sigma 1 equation. Remember kan? I do it again lah, sigma x. Ni equation. You don't have to do more circle kan? Plus sigma x minus sigma y square plus tau xy square. Nampak ke kat saya punya ni? Sigma tu apa? Are you listening, guys? Minus sigma x minus sigma y over 2 square plus tau sy square. Okay, we do have sigma y tak in our case? Ada sigma y tak here? Do we have y here? Ada anything sigma y? No, zero, right? Sigma y 0, right? Ini already done your assignment kan guys kan? Are you listening class? Yes. Tau sy you calculate mega. Okay, tau sy yes we have, sigma x we have. So you got your value of sigma 1. Sigma 2 y is 0, no y 0. Tau sy yes, sigma x. So you get value of your sigma 2. So you just put into the equation yang to calculate your von Mises stress lah. Calculate the calculation. So kalau by axial yang second equation tu von Mises stress equal to square root sigma 1 square plus sigma 2 square. Sigma 2 ni always negative yang tak kan? Negative square jadi become positive. Minus, ni sigma 1, sigma 2. Be careful, sigma 2 ni negative normally. Understand tak kelas? Dia minus become positive lah. Sigma 1 square plus sigma 2 always negative value. Square become positive, minus sigma 1, sigma 2 is negative. Put negative value. And total is 1 square root. That is your equivalent stress, or we call it von Mises stress. Okay, so what is safety factor based on this? Your yield strength. Okay, what material you use? You check from table properties. What value in megapascal over your sigma E. So if your SY greater than sigma E, safe lah. If your sigma E greater than SY, not safe lah. So you mean you have to increase the size of your shaft. Understand? Understand class? Class? Dengar tidak ni? Faham Alright, itu yang tu lah. This is DET. DET is most accurate actually. We calculate the sigma E lah, equivalent stress. And tu, okay, kalau itu the third equation tu, sigma x, sigma y, and tau s. I mean you have, ini consider by axial. Sometimes in our case we have sigma y. Tengoklah depend you punya element that you study macam our. Ada sound? Okay, sometimes in element, you have sigma y value. Sometimes maybe sigma y like this. Ada case. Macam I cakap, macam pressure vessel tadi, radius tu ada, that is sigma y. Tapi rarely lah kita in our mechanical, kalau component design, kita punya project, we have sigma y lah, really happen. Tapi sometimes it happen, you punya element tu ada sigma y, be careful about it. Ada sigma y. Kalau this is the case, you have sigma y, and also you have tau sy lah, tau sy like this, based on torsional. Tau sy ni biasanya torsional. Tau sy. Can you watch my live video nampak Tau sy. You have sigma y also, be careful. Kalau you have this, you use the third equation. Sigma E tu, be careful. You ada sigma x and sigma y. So you have square root sigma x square plus sigma y square minus sigma x Sigma, be careful kalau sigma y you go for tension positive lah, kalau compression mode. Kalau your sigma y is in compression, this one is negative. Take note guys, this one also negative. Negative square square, but this one very important. Negative kalau compression, this is negative. Kalau tension, positive lah. So negative dan negative is positive. Be careful. Kalau this sigma y is negative, negative is positive. Understand tak kelas? Faham tak? Kalau your sigma y ni, be careful. Sometimes your sigma y to go for compression. Compression mean this is your sigma y. And your sigma x go for tension. Sometimes there is a case, your element that you analyze is like this. And you also have tau xy. You have tau xy. Be careful about it. Be careful about it. In your case, kalau you have sigma x is positive, sigma x positive. Kalau sigma y go for compression, sigma y negative. Square is become positive. But this one, be careful. Minus sigma x, minus sigma y. Pasal sigma y is in compression. Kalau both tension, this one positive. Kalau minus time minus, you know ni. Okay, the equation is plus 3 tau xy square. Square root of it. Ni dia punya equation. So you put into this one. Sigma. Tapi this one rarely happen lah. Tapi kita banyak by axial stress. Normally kita banyak by axial stress. By axial stress, okay. Remember yang you punya assignment kan guys? And you punya assignment I mention again. You have like this. Macam normally shaft always like this. Only you have sigma x value. Pasal the shaft along the x-axis. And you have sigma y probably happen, no? This is pointing of your tau xy. Okay, tau xy ni guys. Okay, tau xy ni. Ini depend on your torsion. Be careful about it. This upward, it depend on your punya top punya turning. Tau xy. So you only have, okay, in this case, kalau you only have sigma x and only tau xy, sebenarnya you don't have to calculate shortcut. Kalau you smart, you don't have to calculate the second equation to sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 and square root of it. No, you're not necessary. Kalau you have biaxial, you only have sigma x and you only have tau xy. Straight away, you can calculate your equivalent stress like this. Sigma x square plus 3 tau xy square. Are you listening? Sigma x square plus 3 tau xy square. Square root of it. That's will be sigma equivalent. So safety factor is your yield strength of your sigma equivalent. Yes, that will be your safety factor. Okay. Right, okay, look back on the slide. Okay, okay, consider, okay, another thing to consider. Okay, tadi maximum shear stress theory is said that shear strength equal to 0.5 of our yield strength. Tetapi, but in distortion energy theory, the relation of shear strength, boleh dengar and yield strength is not 0.5. It's not 0.5. Okay, the most accurate. Pasal distortion energy theory is the most accurate to predict yielding, to predict failure for ductile material. So we need to relate. Kalau since distortion energy theory is the most accurate, we need to relate based on these theories, the relation between yield strength and shear strength. Okay, yield strength. So actually, what is the most accurate value of shear strength? Shear strength in DET is 0.577. So since why to explain why is it 0.577? Why? Okay, kalau if you look, consider kalau you punya, if you look on my live video, you have pure torsion. Okay, this is your specimen. You only have pure torsion punya case. Only pure torsion. Only pure torsion. Torque and torque. Only pure torsion. Okay, your element is along your circumference. Your element become like this. Your element, you have pure torsion. So this downward. This one, the left, upward, top. So you balance like this, balance like that. So this will be your tau xy. And we don't have any sigma because this is a pure torsion. When we plot our Mohr circle, when we have pure torsion, we don't have sigma x. So our, okay, this is x-axis. Boleh dengar? Boleh? Boleh dengar kelas? Okay, for pure torsion, if we plot Mohr circle sigma over tau, okay, on our x-axis, we don't have sigma 0. Okay, and we have shear stress, can we have shear stress based on torsional stress. Shear stress is clockwise positive. So this is our point x. On y, we have nothing, no sigma, 0 also, but our turning of shear stress is go counterclockwise, negative this point y. So it means our Mohs circle at the origin, okay, at the center. This is our pure torsion Mohs circle. So this will be our sigma 1, this one, sigma 3, we have tried, sigma 3 is 0 as you guys, and this is your sigma 2, sigma 2. So it means sigma 1 to equal to negative sigma 2 lah. And you punya tau max equal to sigma 1, betul tak? Your tau max equal. Because why? Why I'll explain? We need to explain. Because since DET is the most accurate to predict yielding, so we need to relate. Pasal based on maximum stress theory, shear strength is 0.5 SY, but DET is the most accurate. DET different than MSST. So DET said, okay, because we have our sigma equivalent, right? Sigma equivalent. So fella, kalau based on ni, sigma equivalent that we calculate in DET kan, dia punya limit dia is SY lah. It cannot be greater than SY. So the limit strength dia SY. Okay, kalau pure torsion, kalau kita punya, okay, kalau untuk kita for calculation of sigma in DET kan, sigma E is sigma 1, sigma 1 square plus sigma 2 square minus sigma 1, sigma 2. And this one totally square root. And totally square root. Kalau kita tengok Mohs circle, we relate to this. Kita relate this sigma 1 ni, this is sigma equivalent. Sigma 1, we relate to this Mohs circle. Sigma 1 and kita punya apa? So this is our tau maximum kan. Sigma 1 equal to tau kan. Pasal kita nak relatekan shear strength guys. Kita nak relatekan shear strength. It means the tau ni equal to sigma 1, betul tak? Equal to sigma 1. Kalau untuk case pure torsion, for pure torsion case, our tau ni, the maximum value of our stress tau ni equal to sigma 1. For Mohs circle, the principle lah, our principle tau maximum equal to sigma 1. This is tau max lah, and the tau. So it means kalau kita replace, so this one become tau square plus, okay, sigma 2, since it's in negative, tau is our tau maximum, right? Tau maximum equal to negative sigma 2 lah. Negative tau lah. This one is negative tau square minus sigma 1 is equal to tau and sigma 2 is equal to negative tau. Kalau itu we substitute the tau value into here, we get total is, we got apa, 3 tau square root. 3 tau square root. Pasal we need to relate to shear strength, because tau maximum relate to shear strength. We can say what is shear strength value relate to SY for DET. So we replace into equation of DET punya equivalent stress. We replace by consider pure torsion. So this tau equal to sigma 1, tau equal to negative sigma 2. Okay, negative sigma 2 equal to negative tau. Pasal sigma 2 is negative. So we substitute the value. We got the sigma equivalent. Sigma equivalent equal to square root 3 tau square. Okay, 3 tau square. Okay, so it means, okay, let's consider since, okay, sigma equivalent equal to, okay, square root, I just make it outside, sigma 3 and this one, tau lah, pasal ini square root tau square become tau lah, sigma equivalent become, okay, sigma equivalent, dia punya limit dia is SY kan, sigma equivalent, the limit is yield strength, tau limit dia is shear strength, betul tak? Tau limit dia shear strength, okay, limit, I mean limit border before failure lah, border to failure is shear strength. Limit dia SY, ini limit dia sigma E, if go to SY, start fail lah, yielding berlaku. So relate shear strength any, so from here, shear strength is, from here, SSY, okay, since SY equal to square root 3 SSY, so shear strength equal to SY over square root 3. So equal to, so SSY equal to 0.577 SY. 1 over square root 3, 0.577 SY. So ini yang you kena take note. Based on DET. So ni kawan, nanti kalau you nak want to get what is the strength, sometimes in Brittle. So based on DT, your shear strength is 0.577 SY. So already explained in your slide, dalam slide ni ada explain you punya ni, SSY shear strength. Shear strength is 0.577 SY. So ini one kena take note on this. But we know satu lagi formula yang safety factor for DET, you know lah. N is SY over sigma E. So ini DET punya formula lah. So you kena ni. And also shear strength is 0.5. This is the most accurate to predict shear strength. Pasal based on MSST 0.5, still not that accurate. Pasal DET the most accurate energy to distort change the shape but not the size. That's why we call sigma equivalent. Based on distortion energy. It's called distortion energy theory. Okay. Okay, when you plot yang ni, kalau dia punya plot of the DET dia different dia like this. The DET dia ellipse. Kalau plot sigma 1, sigma 2 of DET, this is your sigma 1 over sigma 2. It is not more circle plot, guys, not sigma or tau. Sigma 1 and sigma 2. Remember, kalau data material, we have zone of SYT and we have zone of SYC. SYC. Kenapa dia punya about the same size? Pasal for ductile material, SYT and SYC is about the same. But not brittle. Kalau brittle dia punya, pasal MSST brittle. Hold on, let's start that record. Yeah, alright. Brittle, kalau brittle, I'm not talking about data. Brittle, dia punya SYT dia, SYT, SYC lagi besar. Compression, brittle. I'm talking about brittle. Kalau you buat specimen test, you brittle material like cast iron, you buat tensile test, the force to make tension is lower to make it break rather than the force of compression. It means for compression to make it break. The force of compression, etc., to make it, for brittle material to make it break, is much greater. So SYC is balloon in negative is much ni. Ini kalau untuk brittle SYC is much greater than, is less than SYC. Macam tu. Ini you plot sigma 1 and sigma 2. Ni maximum normal stress theory untuk brittle. Brittle. Kalau you use brittle cast iron, you punya specimen cast iron, you use this one. You use this one for this. Okay. Okay, as I explained tadi, okay, untuk DET, untuk DET yang plot of SYT, SYC, so I'm talking to you yang tadi, kalau ductile, pasal dia good for ductile material, dia kind of square. SYC and SYT value is about the same. Tension, and ni adalah SYC. Since, kalau MNST, tak, you can predict failure using MNST normal stress untuk ductile material also can, tapi not that accurate. Rarely will ask you about that. Okay, tapi MSST, remember that your MSST, this diamond shape, your punya zone is your diamond shape. But for DET, okay, ini adalah MSST kan, ini adalah MNST. But for DET, you punya zone is ellipse. Kalau you plot graph sigma 1, sigma 2, you draw, macam mana you draw ellipse? You belajar engine drawing kan. You know the value SYT, SYC, SYT, SYC, you get for the table properties. And you plot the graph. Macam mana kita draw ellipse, guys? Belajar engine drawing. How you draw ellipse? Kan ada ellipse dia punya zone macam ellipse. Is ellipse. Pasal the engine already plot, ASME already plot all the data on the ni within this zone ellipse. So they will be your magic axis, this ellipse. Dia lalu all this point. Dia lalu this point. Dia lalu this point. So this is within. The ellipse within, the ellipse is you punya safe zone. Safe zone, sigma 1 and sigma 2 plot. Sometimes kenapa, sir, we have to plot sigma 1, 2, we have formula. Formula ni, you cannot see the location. Sometimes you are in compression mode. From here, you can know. You pasal based on graph, you can predict. Either you are in sigma 1 in 2, this one in compression. You can the zone, where are you? It's much better visually to visualize. Okay, tapi in shortcut, you can use formula lah. Pasal kita boleh predict failure based on graph ni, sometimes we can predict, we can make judgment at mana kita punya border area tu situ. Based on sigma 2. Okay, mean kalau you punya sigma 1 and sigma 2 plot within this zone, so it's safe lah. You do this graph, this is the way, okay ni. Ini kalau ini adalah, ni of your sigma 1, this is your sigma 2. So this is you intersect ya, this is a border of your S2 lah. So yang ini adalah you intersect ya, ini adalah border your S1. Safety factor is S2 over sigma 2. Okay, boleh nampak sekarang? Okay, boleh dengar saya? You can predict failure by using ni lah, S2, sigma, S2 over sigma 2 or S1 over sigma pun boleh. Atau you can question lah, where SY over your sigma equivalent, that's your safety factor. Okay, faham kelas about failure theories, 3 teori, ini saja 3 teori yang kita pakai. Understand kelas? Ada question tak? So this is zone combination Yang ini ada shear diagonal line shear diagonal line ni where your sigma 1 equal to negative sigma 2. On shear diagonal line you punya pure torsion tu you punya diagonal line. So this is a zone. Okay, I think that's all for explanation about the theory. Ada apa-apa question? Okay, you punya case for example like this guy, kalau if you look on the, remember I give you yang example in class tu? Example that I explained in class. Are you watching my live video? Yang ni. Class. Hello?
Yes.
Kan example that I explained class. Okay, let's say lah dalam soalan give material, just in case you want to know macam mana application to find safety factor for this case. Okay, let's say what is the diameter? Diameter is given, right? What's the value that soalan tu suruh buat apa? Hold on sekejap. I got to check balik. Actually the soalan tu, the one I explained to you to draw the more circle, right? More circle and okay, we draw more circle on XY plane and XZ plane. Then we need to find the apa tu dia punya principal stress, am I right? Principal stress. Hold on, saya hold on sekejap. Where is it? Yep, yeah, this one. Yes. Let me check. Hold on sekejap. Banyak sangat kertas ni, saya tak teratur. So we have our maximum stress is one. Okay, we have to do. Okay, tengoklah yang macam you punya this one. Okay, you punya assignment that I explained in class, sample problem. So you have this kind of system, right? And we find that point B is the most critical lah. You can see my live video boleh nampak SY plane, we do shear diagram. Okay, XY plane on the top view. Okay, on the top view, okay, for example, is XZ plane first. XZ plane is when we look from here, so we got the value of shear diagram like that. So we got our MB is positive, any 150, B is have 150,000. Okay, so at XY plane, if we look from the top, okay, we got like this, and at B is negative 25,000. So we combine, B is most critical compared to C, and we combine the total moment at B 25,000 square plus total moment at B 150,000 square. So we get the total moment is, what is it? My calculation total moment is mana dia? I got to find the kertas sekejap hold on sekejap. The total moment Yep, this one. Hold on, yep. Yes. Okay. Right. Then we have we have a total moment at B. Are you listening or not, guys? Are you listening or not? Class. You with me? Kita 2 jam kan, betul tak? Sikit ke? Before we go for internet. Saya dah finish my lecture to okay, ada sound tak sekarang? Ada Boleh dengar saya? Okay, remember, okay, at B, kan previous example, same goes for your assignment. Your assignment only one plane, only exact plane, if I'm not mistaken. In example that I showed in class, we have 2 planes. So we find out at B, 150,000, and the one is negative 24,000. Then we find the total moment at B is 152,069, the most maximum at B. And not as so we focus at B lah. B is the most critical lah, compared to C. So we get the total moment at B. So it means at B too, we have, okay, it means at B. So also at B tu kita ada, hold on jap, saya ambil kipas sekejap. Okay, tengok sini. So at B, so it means at B, okay, element at B pasal shaft tu, okay, the shaft tu is like this guy, the shaft tu. So we have this one. Okay, at B. Okay, kita tengok diagram ni. At B tu, okay, at B tu, kalau kita tengok, if you look on the exact plane, kerana ni ada student tanya saya, sir, which one, kenapa suppose ni, ada correction, maybe Inkra cakap atas station tu, but I think atas is compression. Kalau you tengok the exact plane at B, okay, exact plane, the 4,000 is pointing downward, so the shaft tu tends to bend like this lah. Okay, at exact plane tu where it's looking this front view lah. So at B2, because of 4,000 is going to support by bearing here, and this 4,000 exact plane, the shaft tu tends to bend like this, betul tak? Bends downward. It mean bawah dia tension, But if you look at the top, XY plane, the diagram for explain like this. So at B, so we have AY like that, because the 2,000 ni like bending the shaft to upward. I mean atas dia tension. Kalau we look from the top, at this atas dia tension, looking from the top. So that we combine moment at both planes. When we combine moment at B, it means we combine, kalau we look at exact plane, when we look at exact plane, the 4,000 would tends to bend downward. I mean atas ke atas dia compression. Okay, atas dia compression, bawah dia tension. But at XY plane, looking from the top, the 2,000 means okay, for XY plane, looking from the top, this side, the top portion to become tension, bawah compression. I already explained. When we combine moment, That's why when we combine moment at section B, okay, in this section B, I zoom in, B. So the direction of moment, since we look at as exact plane, okay, exact plane, the moment is 150,000 positive, 50,000 positive. So since this is X axis, and kalau ikut soalan, this is Z axis, okay, yang ini adalah Y axis. Okay, yang ini 150,000 XY plane, exact plane, means that okay, the direction is Y positive, pasal the moment is positive exact plane. So you punya, since your moment positive, kalau Y plane, so it mean the turning of moment is like this, but you punya vector moment ni M, my, direction is my, where it is 150,000 Newton millimeter. Okay, but the SY plane, you punya moment at B is negative. Moment is negative. So moment negative, it means your moment negative on Z. So it means that you punya moment negative on Z, the value is, moment ni adalah negative 25,000. Why is negative? Pasal Z is pointing up, so dia pointing ke bawah. So ini adalah moment yang ini moment on Z. So downward is positive, so is 25,000. I didn't put a negative pasal already consider downward. Downward. So downward, you punya turning is like this. Turning is like this. Turning is like that. So kita punya total moment ni, I'm talking about this portion. Portion ini shaft yang tadi ni A, ini A. Boleh dengar saya? Boleh? Okay, yang ini dia pointing downward, MZ is 25,000. Yang ini pointing this side to positive Y lah. This direction. So you punya total moment ni, vector ni. Okay, you combine kan ni. So this is the total moment. So that's why we ambil total moment at B is 150,000 square plus yang negative 25,000 square. That's why we got moment at B 159. Value dia is 152 kan. Moment, that's why moment at B 152. 152,069 Newton millimeter. Direction of your moment at B yang this one. This one moment at B. Okay, moment at B. Okay, semalam ada kelas dia argue. So, I cakap, okay, kalau when we look here at the side view, section B, so ini yang tadi lah, moment Y, moment Z ke bawah, moment Y. So ini total moment at B. Ini total moment at B. Okay, sekarang ni our neutral axis dah become, are you watching guys? Our neutral axis ni combination moment. Understand tak kelas? Combination. So it means, okay, this is our neutral axis already slanting at an angle. Theta you can get lah inverse tangent my over ni lah, mz of my, 25,000 over 150 inverted, you can get theta. Okay, this is our neutral axis that become like this because our moment dah yang ini, total moment pada this angle, this one. So kalau the student argue, sir, is the, okay, sekarang ni our side ini atas dengan bawah portion yang critical. Adakah this one tension or compression, dia ask me. In logic apa? Atas compression or tension atau bawah compression? Which one is tension, which one is compression? Are you with me, class? Sikit je lagi, sorry sikit je masuk. Class? You understand me? You understand my question tak, class? Class? Yep. Okay, because the moment is like this, because this moment our turning is this. So atas, which one is tension, which one is compression? Yeah, you are right. Atas is compression. I already mentioned in class yang atas tension, sorry. Atas will be compression, bawah will be tension. Kalau ni, jangan get confused. Okay? Tetapi katakan you mistakenly cakap atas tension, it's okay. Not that harm sangat. Okay, as long because we need to study, okay, we go for tension. Either, okay, let's say our perception wrongly, supposed to be atas is compression kan, we say atas is tension. It's okay. Tapi our element, okay, either atas atau bawah, kita go for tension side, betul tak? Okay, any element or any top portion or upper portion, okay, we go for tension because tension is the most critical. This is our element like that. So this is what I call sigma x. Understand class? Sigma x, so total moment, sigma x ni 32 moment pi d cube. Kan? Total moment pi d cube, Total moment pi d cube. So moment total moment at B yang this one, 152 ni, you put into here. Okay, so you put total moment, okay, if I write the equation, okay, satu lagi, we have torsion, right? We have torsion. The diagram ni guys, I cakap kan, you punya SY plane kan, you ada torsion kan? You have the torsion between B and C, you have torsion. Torsion. So if you look on the, based on the question, okay, if you look on the question, okay, at B, okay, just the left of element B to the left of element B, because the torsion, basically, first you have torsion, the left of B torsion is like this. Actually, between A and B, no torsion. I mean, the left of B, still before, just at B, initial at B, the left of it equal this direction, downward. But to the right of B, the cancel out by C torsion is yang the 2000 Newton times the radius 50 of this bigger pulley. So it's upward. So it means your element, the right of element here to be upward lah, like this. The left yang go downward. Understand? Ini kena tahu juga. Ini yang tau, we can say it tau SY. Tau SY. Where this tau SY is 16 torque over pi d cube. Okay. Okay, the point is yang I explained to you just now about failure theories. Kan? Okay, you want to predict in DET here. Okay. We know that sigma x, okay, hold on. Sigma x, kita tahu, okay. Sigma x berapa value? 32 moment b pi d cube. Okay. So what is the value? 32. What is the moment? 152. Calculate for me guys. 069 ni Newton millimeter kan. Okay, over pi. Okay, let's say kita give the diameter is 30 millimeter square. Cube Let's say the diameter of the shaft. Okay, let's say kita design. Diameter is 30 millimeter. So diameter is 30 millimeter. So what is the value here? Calculate for me. 30 cube Okay, ada line. Sorry Okay, sikit lagi. Sorry. Okay, sigma x apa? What's the value here? Bending stress, sigma x. 5? 510 57.4 megapascal, right? Megapascal. Alright. Okay. What is tau xy? Tau xy is 16 torque over pi d cube. Okay, torque we already given, already calculate, right? Torque is the ni lah. Actually, torque is the 4000 times the radius lah. Torque is already calculate, right? Torque apa tadi? Torque 4000 times berapa? Yeah, torque. Torque is, yeah, I already calculate already this thing. Okay, torque is because torque is apa? Torque is 100,000, right? 16. Okay, the force times the radius, 100,000 meter. So 16 times 100,000 over pi 30 cube. So we got 18.9 megapascal. Alright, class, understand that? Faham class? Okay. So since our element is like this, okay, we got yani 57.4, okay, and tau is I cakap tadi dia downward and AC. Yalah. Okay, since our element is like this, our element tu, okay, our element, so ini is sigma x, okay, sigma x and tau xy is upward, to the left is upward, tau xy, ini downward, tau xy, okay. Okay, understand? So sigma x we already calculate, tau xy. Okay, where is DET? Based on DET, safety factor is what? Safety factor is SY. What is your sigma E? Sorry, sigma equivalent equation apa? What is sigma equivalent? Sigma equivalent equal to square root sigma x square plus 3 tau xy square. So what is it? Calculate for me. Sigma x square apa? 57.4 square plus 3 times 18.9 square root of it. Berapa dia punya nilai? Berapa? Are you listening? Are you watching my video? Equal 60.1. Okay, let's say kita consider dalam this equation kita cakap we want to use material AISI for the shaft 1040 hot roll. Okay, ada masa tak tengok? Okay, hold it sekarang. Kita tengok textbook. Can you open your textbook tak? Textbook, Jabina. Can you watch my textbook? Ada nampak? Kelas? Okay, it is at the back of your textbook, table material properties. Oh, hold on, too much. AISI, what did I mention? AISI 1040 hot roll, Next. Where is it? Ni 1040. Not this one, I want to use this one. 1040 hot roll, mana dia? Yep. 10, okay, you can use 1020, 1045 hot roll. Boleh lah, let's say I say I want to use material, carbon alloy steel, 1040 hot roll. Nampak tak guys, ni, kelas? Can you watching my textbook? Kelas? Yes. No, this one ultimate. Can you line putus? Okay, boleh nampak tak saya punya ni? Yield strength dia berapa? In megapascal, this one. 414 plus 414. Okay, the SY is 414. So tadi mana kita punya? Tadi you cakap sigma E is, okay, can you see my live video? You nampak kan? Sigma E 60.1 kan? Plus. We calculate kan, sigma X square plus 3 tau X square. So you got sigma E 60.1. So safety factor N safety factor equal to SY over sigma E. So SY is what? 414 over 66.1. Berapa? Berapa? 414 over 66.1. 6.13. Safe lah. Okay? Safe. That's how you calculate. Itu je lah. Value static. We still assume static. Actually, shaft is static itu later on week 4. Understand tak, class? That's how you do it. Tapi your assignment that I give you for assignment, you don't have to calculate safety factor. You plot shear diagram, moment diagram, and also get the principal stress. That's it. Tapi kita, okay, next class we go for sample problem. So there's the application of it lah, DAT. Just straightforward, safety factor SY over sigma E. So it's safe. I mean the shaft, if I use AISI 1045 hot roll, so it's safe. And the diameter of the shaft that I design is 30 mm. Safe lah. 6.13 is safe lah. But if you get 1.0 something, that one is not considered safe. Actually, theoretically, 1 is border of failure, right? Below 1 fail. If you get 1.2, 1.3, 1.5, actually it's not that safe. Because there is a lot of uncertainty. So we have to make our safety. Do not make your safety factor 100, 200. It is too much, wasting material. Macam 4 is okay. 4 and over. Maybe sometimes we may consider 2 point something lah. It depends on the situation based on experience. Biasa normally experienced engineer will tell you to the fresh engineer what is the facility factor to be considered, but not 1 point something. And 1 point something is actually not that safe. Okay. Macam lain this calculation 6.13 is safer. Banyak student project, safety factor 67 point something, ada 100 point something. Itu too much lah. I make this one too much. You have to reduce down your material. You are wasting material too much, too strong. And so you might ask, so what is the best setting? Actually based on experience, based on not 1 point something, actually not. It's actually 2 point something. Kita tak ada that is no margin or this ni. Okay, that's the one best way to design. Kita assume dulu safety factor. Macam saya cakap, you assume dulu safety factor is 4. Then you punya all the variable of you punya stress will be variable diameter. Then you get what is the diameter. Itu one shot you punya calculation. Dan terus. Kalau in this case macam the one that I show you, we design, kita put the size lah. I put the 30, I put the material 1045 hot roll. So the luckily I got safe. If I not safe, I mean I have to increase the size of my diameter shaft, then I have to recalculate again. And also I have to change material. Tu kita ada dua. One first case is kita assume safety factor, pilih material, and then we get the diameter of the shaft. Or number two, kita like the one that I show you lah. Kita pilih diameter of the shaft and the material, and then we get the safety factor. So this is DET. DET is SY over sigma. Okay, class. Sorry for taking your time. So kita see you on the next class. Okay. So I go for internet. Ini section 8 ya? Section apa ni? Oh, 23. Okay. Boleh nampak kan? Can you scan your attendance? Okay, Assalamualaikum warahmatullahi